Folks, welcome to the next episode of Electromagnetism. Today we're going to solve yet another problem dealing with the Laplacian in rectangular coordinates. But today's problem is not only going to be in 3D, but it's going to involve a rectangular box where only half of a face is held at a non-zero potential. Let's get started with the Laplacian.
You said it's a slow ride, everything's gonna be alright. All I gotta do is just hold tight, everything is gonna be fine.
Alright folks, welcome to the next episode of Electromagnetism. Let's begin with today's lecture. Today we're going to review the usage of the Laplacian in rectangular coordinates for 3D boundary surfaces. Let's begin. Recall that Laplace's equation starts with the Poisson equation, which says that nabla squared of the electric potential is minus the volume charge density over epsilon naught. Where does this come from? Well, I've shown it many times, but it comes from the divergence of the electric field being equal to the volume charge density over the permittivity of free space in a vacuum. Okay, now I've shown how Gauss's law, plain and simple, the divergence of the electric field can lead to this by simply substituting in the electric potential for the electric field. Now, if you're dealing with a situation in which the volume charge density is zero, then and only then do you have the Laplacian, which is when the right hand side is zero. And how do we solve the Laplacian? Well, first let me answer how we solve the Poisson equation. Poisson's equation we solved, and we got the equation for the electric potential of a continuous charge distribution, which we found to be the integral of the volume charge density of that distribution over R. And of course you have your 1 over 4 pi epsilon naught and your d tau over a certain volume. Okay, now where does this come from? Well, notice this rho times dt is simply dq, right? And this r is simply the distance from which your source charge is to where you're measuring the potential. In other words, if I draw a picture, maybe it'll make it more clear. Let's say we have a volume charge distribution as follows, some kind of a arbitrary volume in which there are charges situated, and we seek to measure the potential at some distance from the origin. Call it r. We'll call it r field, okay, because that's where we want to measure the fields. But where are the source charges? The source charges are inside the volume, right? They're right here, r sub s. And the distance between these two, r sub f minus r sub s, that's the distance which appears right here. The distance, in other words, between where we want to figure out the electric potential and where the source charges creating the electric potential and the electric fields originate from. So, in other words, all you have here is k, 1 over 4 pi epsilon naught, q, rho times d tau, over r, which is the radius between where the charges are and where you want to find the electric potential. That's it. Very simple. Okay, but now the right hand side is zero. Now how are we going to solve Laplace's equation? Well, check out the last 3 videos to see in-depth derivations for the solution to Laplace's equation. But in this lecture, I'm going to very quickly review how we solve Laplace's equation. We assume that the electric potential is separable. In other words, that it may be separated into a function of x and y of y. And then we plug this back into here, and what do we get? We get a second order partial differential equation, which has the form x double prime over x plus y double prime over y is 0. Now, in today's problem, we're going to be solving the 3D Laplacian equation. So let me add in the z coordinate. So z of z, and so that's just going to add one extra term to our partial differential equation. So plus z double prime of z equals 0. So I say partial differential equations, but technically there's only one variable, so I guess it's an ordinary differential equation. So here we have our ODE, and the only solution to this is when x, y, and z are constants, right? If you have 3 functions of 3 different variables, all summing to equal 0, the only way that can happen is if each of the 3 variables are equal to constants. And so you must choose your constants wisely. Why? Well, your constants must be chosen according to your boundary conditions, right? These are very important when solving electric potential problems. boundary conditions. Your boundary conditions are going to determine what kind of function is going to hold for the electric potential in the x, in the y, and in the z directions. You will always have either an oscillating combination of sinusoidals or a non-oscillating combination of exponentials for your x, y, and z direction electric potentials. Whether it is a sinusoidal or an exponential depends wholly on your boundary conditions. After you choose your boundary conditions and your three functions, you're entitled to write down your full electric potential, V, in terms of a linear combination of x of x, y of y, and z of z, all times an expansion coefficient c sub n. Now, in this case, we have three dimensions, x, y, and z. So I'm actually going to need two summations, one for c sub m and one for c sub n, right? So I'm going to have two summations, one taking m equals 1 to infinity and the other taking n equals 1 to infinity. And this is going to be your electric potential. This is going to be your second to last step, but there is one more thing that remains, and that is figuring out the expansion coefficient, this c sub mn. How can we figure out c sub mn? Well, Fourier's trick saves the day. Multiply both sides by the integral of, let's say, 0 to a of sine of n prime pi. Let's use x, just arbitrary, but if x was indeed the oscillating direction, then that's what we'd use. N prime pi x over a dx times, now there's two, since we have three dimensions, there are two constants and now two integrals, right? So another integral for 0 to b of sine, and notice that these are primed variables, so that when you integrate these and the sinusoidals from the potential come in, it's going to kill everything except when n prime is equal to n. In that case, it's going to reduce all the integrals to a over 2 for this case, and b over 2 for this integral. So for this integral, you'd have something like m prime pi y. I'm just choosing arbitrarily, but maybe y is your oscillating direction for this problem, dy. So once you multiply both sides by these two integrals, you'd be reducing all the integrals to something like a over 2 and b over 2. And that is Fourier's trick. All right, folks, so that is a brief summary of using the Laplacian in rectangular coordinates for 3D problems. Now let's check out today's problem. Here is another view of problem 1. Let's check out problem 1. Alright folks, so here's our problem. A semi-infinite grounded conducting rectangular tube has a cross-sectional area of A times B. The left-handed end of the tube is arranged to have a constant potential when x is between, or rather when y is between 0 and a over 2, but z can be anything, but it's grounded when y is between a over 2 and a. Okay? Now find the electric potential everywhere in the tube if there's no charge in the tube. Now, of course, if there's no charge in the tube, well, what do we have? Well, we have the license to use the Laplacian equation. Nabla squared V equals 0, right? From Poisson to Laplace. Very important to see the distinction there. Poisson, you do have a volume charge density. Laplace, you don't. There is no volume charge density inside the area you're interested in, right? So, Nabla squared V is 0. We assume that V is separable, so it is x of x times y of y times z of z. And now we end up with that differential equation, x double prime over x plus y double prime over y plus z double prime over z equals 0, which leads us to a junction, right? At which point we have to choose, okay, x, y, and z. Are they going to be exponential or oscillating, as in a sinusoidal? To answer that question, we have to examine the boundary conditions for this problem. So let's go ahead and write down our boundary conditions. Okay, boundary condition 1. Let's see, what is the easiest thing to start with? Well, we know that the rectangular plate has almost every side grounded. But check it out. First of all, it's an infinite rectangular plane. So just right off the bat, we know that as you head in this direction, the electric potential is going to start dropping to 0, right? So as you head for larger and larger x values, your V values, your electric potential values are going to start dropping as you go farther away from this plate held at a potential of V naught. Okay, so that's one thing I noticed. So let me write it down. As x approaches infinity, the electric potential should approach 0 because of course there's no charge in the slot to help it go up again. So what about in x equals 0? When x is 0, it's totally up to y, right? If y is between 0 and a over 2, then v is held at a constant potential. If it's between a over 2 and a, then there is no potential, right? It's grounded. So let's write it down. So boundary condition 2 is that when x is 0, but y is between 0 and a over 2, and z can be anything, then the electric potential is V naught, not 0. But when y is between a over 2 and a, then the electric potential is equal to 0 because that part of the back face is indeed grounded. What other conditions do we have? Do we have any conditions on z, for instance? Well, we do. This bottom face and this top face are both grounded. So let's write that down. For z, we have the condition that the bottom face, which is x can be anything, y can be anything, right? I can move all around this plane, but it doesn't matter. When z is 0, the potential had better than be 0. And the fourth boundary condition, when I move to the top face, once again, this face is grounded as well, right? Everything's grounded except this V naught on the back. This is also grounded, so when x is anything, x can be anything, y can be anything, but when z is a, then my electric potential had better be 0. Okay, so when I move b units in the z direction, my electric potential is 0. When I stay on the xy plane, my electric potential is 0. Is there anything else where my electric potential is 0? Right off the bat, it doesn't seem like it. It seems like we have these 4 boundary conditions, so I'm going to run with it. Okay, so based on this information, can I deduce if the x, y, and z functions will be an exponential or a sinusoidal? Well, indeed I can. Let's start off with the easiest one. Let's start off with z. I see that z must start at 0, and when I reach b units up, it must end at 0 as well. And so that means z must be a sinusoidal because that's the only kind of function that repeats itself, that has periodicity. What about in the y or x direction? So let's look at the x direction. In the x direction, I've got to start at some potential v naught, but as I go to infinity for x, then my potential heads off to 0. So it seems like I should use an exponential for x. What about y? Well, as I head in the y direction, first, when y is 0, this left face I have not created a boundary condition for. So I'm missing some boundary conditions. This left face and that right face. So let's consider those boundaries. That on the left face, when y is equal to 0, x can be anything, z can be anything, but when y is 0, my potential had better than be 0. So x can be anything, y has to be 0, z can be anything, the potential has to be 0. And finally, on the other face, this back face right here, or right face, depending on your perspective, when I travel a units in the y direction, you can see that my potential has to be 0 again, right? So the potential when x is anything, but y is a, and z can be anything, is also 0. Okay, so let's take a look at y now. So y has to start at an electric potential of 0 at y equals 0, and it has to end at an electric potential of 0 when y is a. So that means y too is returning to its previous electric potential value, hence it must be a sinusoidal. What about x? Well, let's take a look at our x values. When x is 0, we have nothing to worry about, right? X is 0, everything is fine. But as I move along this plate, x is 0, but y is between these two, y being between 0 and a over 2 means I have a constant potential V naught. Between a over 2 and a means I have no potential at all, 0 potential. So it depends on my y value what I should put down for x, right? So let's come over to here, for example. When x is 0, I say, y is between 0 and a over 2, the electric potential is V naught. But when x is 0 and y is between a over 2 and a, the electric potential is 0. Hence, x does not return to its original value, right? It starts going down, 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 and at some point in infinity, it heads down to 0, right? At some point down to infinity, it heads down to 0. So that means, this is a hint, that x must be an exponential, okay? So there you go. Now let's go ahead and write this stuff down. So for x, we know that an exponential function looks generally like a to the e. Now since I have two coordinates here, two constants, k and l, let's call them, I'm going to have square root of k squared plus l squared times not z but x. And if you want to see where this exponential's power comes from, just check out the previous lecture where I detailed step by step where this power, where this exponent comes from. Okay, in short, it just comes from ODEs. If you differentiate this twice, you'll get k squared plus l squared here, minus k squared here, minus l squared here. They add up to 0, as should be when you use the Laplacian. So this plus a decaying exponential is going to be our gamut, k squared plus l squared to the x power. Create a combination of sinusoidals this time. So I'm going to have c sine, let's use k, y plus d cosine ky. And finally, for z, I will have something like e sine l. So I have to use my other constant, z, plus f cosine lz. Okay, so I've got everything on the table. Now all we have to do is use our boundary conditions. Let's enforce those boundary conditions and get rid of some constants. So here we go. Let's start with the x direction. So in the x direction, what is happening? Well, in the x direction, when x heads off to infinity, x heads off to infinity, as I go for larger and larger x, my potential should be decreasing, right? So I should not have a growing exponential here. Hence, this a must be 0 by the very first boundary condition, by boundary condition 1. Okay, so we don't have this term at all now. This term is gone. Okay, what else do we have? Let's take a look at y now. For y, these are our boundary conditions, and this condition says that when y is 0, my electric potential should be 0. In other words, if y is 0, I will have c sine 0 plus d cosine 0. Sine of 0 is just 0. Cosine of 0 is 1, so d must be 0, right? If you want to see me go step by step through that process, you can just watch the first lecture where I do that. But in this one, if you just plug in the boundary condition 5, sorry, not 2, if you just plug in boundary condition 5, you will observe that d must be 0. Okay, what else do we have? Let's take a look at z, the electric potential in the z direction. In the z direction, what boundary do we have? At z equals 0, my electric potential should be 0. So likewise, cosine is going to prevent me from having a 0 potential at z equals 0. So I must kill it. F, the constant f, therefore must be 0. So f is 0 by the third boundary condition. Okay, so now we have cleaned up most of our functions. So this term is gone, this term is gone, this term is gone. And we have applied boundary conditions 1, 3, and 5. 1, 3, and 5. But there are a few more left to exhaust. Let's take a look at boundary condition, let's say 4. When z is b, then my electric potential is 0. What does that tell me? That tells me nothing less than the value of this constant, L. If you look at our previous videos, you'll see that plugging in z equals b tells me that E sine LB must be 0. So LB must be a constant of n pi. So L must be n pi over b. By which boundary condition? This is boundary condition 4. By boundary condition 4. And so we have used boundary condition 4, and let's now use boundary condition 6, which tells us that when y is equal to a, our electric potential is 0. So when y is equal to a, electric potential is 0, means that k, the value for k is m. I'm using a different constant, notice not n, but m pi over a by boundary condition 6, vi. And there you go. We have definitely simplified and specified what our constants are by enforcing all boundary conditions except this last one, which, hint hint, we'll use in the last step when we try to determine the expansion coefficient using Fourier's trick. So now what I'm going to do is erase most of this stuff except my electric potential in the x, y, and z direction. All right, so let's keep on keeping on. What are our electric potential functions now? Well, let's use blue. For our potential in the x direction, x of x, we have a sine. Oh, actually this is an exponential. So it doesn't matter what you call your constant. It was b there, it's a here, who cares? So it's a decaying exponential with the power of k squared plus l squared, but now I know what k is. K is m pi over a squared, and L is n pi over b squared. You can see I wrote that for L right over there. And all of this times x. And this is a decaying exponential, hence the minus sign here. We couldn't have a growing exponential because that would prevent us from reaching zero potential at infinity. Remember, this is a half infinite conducting box. For the electric potential in the y direction, I have something involving sinusoidals, so I'll have b sine of ky, where k is m pi over a, so I'll have m pi y over a. And finally, for the z direction, I'm going to have c sine n pi z over b. Okay, so I've got everything down, and now I've got to collect everything into one electric potential function. So my v of x, y, z is going to be the summation from m equals 1 to infinity and the summation of n equals 1 to infinity of all of this. But of course, I can pack all the coefficients into one mega giant c sub mn expansion coefficient. And then I can just put down what I've got here. I've got my decaying exponential e to the minus square root of m pi over a squared plus n pi over b squared. Is that right? Indeed it is. And all of this must be multiplied by x. And now let me multiply this by sine of m pi x, sorry, no, not m pi x, m pi y over a, and sine of n pi z over b. Some peculiar coordinates indeed. So now that we've got this, all we have to do is now determine the expansion coefficient, c sub mn. And to do so, I'm going to multiply both sides of my electric potential function, v of xyz, by the following. The integral from 0 to a, well, remember how much of this thing was charged, how much of that back face was held at a constant potential, only from 0 to a over 2. So I'm not going to go all the way to a, but I'm going to stop at a over 2. That's not going to change the value of the integral, by the way, at the end. You'll see what I mean. It does change when you plug everything back in, but let's take it, we'll cross that bridge when we get there. So anyway, we're going to have sine of m prime pi y over a dy, and the integral from 0 to b of sine of n prime pi z over b dz. So these brackets just signify that I'm multiplying both sides by this common thing. So let's go ahead and do it. So on that back face, when I hold x to 0, this x is going to become 0. My exponential, this has become 0, so all of this reduces to 1. And so what am I left with? I'm left with V. Let's use blue for what's remaining. So I'm going to have the potential on that back face, which is V naught, times my double integrals, my integral from 0 to a over 2, 0 to a over 2 of sine of m prime pi y over a dy, and my integral from 0 to b of likewise sine n prime pi z over b dz. That's my left hand side, all of my left hand side. And on my right hand side, remember everything is going to reduce down. I'm going to have c sub mn times a over 2 times b over 2. That's it. See, this a over 2 is still a over 2, even though my upper limit is now half of what it would normally be. So that's what I meant. So now, unless I'm forgetting any terms, all we're left with is, by the way, this should be c sub m prime and n prime right here. So all we have to do now is flesh out these integrals, or you can leave them if you like. That means the expansion coefficient c sub m prime n prime is, this is ab over 4. So that's going to be 4 over ab times v naught times these two integrals from 0 to a over 2. Now I'm actually going to work out these integrals, so let's see what they are. So my first integral is the integral from 0 to a over 2 of sine of m prime pi y over a dy. And my second integral is from 0 to b of sine, almost the same thing, but now with an n prime and with a z instead of a m prime and a y, and a b in the denominator instead of an a. And now let's work out these two integrals. Let's use the right hand side of the board. The integral, hopefully you can still see right here, the integral from 0 to a over 2 of sine of m prime pi y over a dy is going to be what? Well, the integral of sine is just negative cosine, right? So this is simply going to be minus a over m prime pi cosine of the argument inside. So I see that orange is not as visible, so I'm going to resort back to black. So I'm going to have minus a prime, sorry, not minus a prime, minus a over m prime pi of cosine m prime pi y over a, as y goes from 0 to a over 2. Now when y is a over 2, I'm going to have a's canceling out on the top, and so I'll be just left with cosine of m prime pi over 2. So this right here, if you can see all the way down to the bottom, is going to be a minus a over m prime pi of cosine m prime pi over 2. And when y is 0, I just have 0 inside. Cosine of 0 is 1. So that's everything right there. And what about our second integral? Let's work that out as well. I'm going to work it out right here. Let's do it here. So the integral of sine, once again, is going to be minus cosine, but the reciprocal of the argument inside. So minus b over n prime pi times cosine of n prime pi z over b, as z goes from 0 to b. Now when z is b, I'm just going to have cosine of n prime pi. And when z is 0, then I'll just have cosine of 0, which is 1. So now let's write down our final answer for the expansion coefficient, c sub m prime n prime, which is going to be 4 v naught over ab times minus, see this minus and this minus cancel each other out. So I'm going to have a times b over m prime times n prime, pi times pi, which gives us pi squared. And now I'll just have the cosine terms, right? So ab's cancel out very nicely. And so inside I'll have that factor of cosine, which is cosine of m prime pi over 2 minus 1. And the factor of cosine that comes from here, which is going to be cosine of n prime pi, cosine of n prime pi minus 1. And this, ladies and gentlemen, is our final answer. If you'd like to tidy it up, you certainly can, but this is our final answer. Thank you for watching this lecture on the Laplacian equation, and we'll see you in the next one.